I'm going to be talking to you about multi-sensory display of multi-dimensional data. So yeah, just to explain who I am, I did my physics undergraduate in Bristol, and recently submitted my PhD also in Bristol, and now work for the government in the Department of Energy Security and Net Zero as an energy engineer, which is one of those kind of job titles that's not very descriptive, but it sounds kind of fun, right? But today we're going to be looking at different ways of representing data. So I'm sure you guys are into graphs because you're here, right? But this is a fun example. You might have seen this before. This is a nice example of why graphs are really helpful. So these are 4 different data sets from famous stats textbook, which all have the same number of items, the same mean of x, mean of y, the same linear fit. All of those values are exactly the same for each of these data sets. But just looking at them, it's hard to really see how they distinguish themselves from each other. But if you plot them on a graph, it becomes immediately apparent that these sets of numbers are telling very different stories, even though they might look the same if you just do some basic statistics on them. So another reason we like graphs is because it lets us see things that you might not notice otherwise. Does anyone recognize this graph? This is a very famous graph. It's from the 1800s at the back.
Blanking.
Cool. Yeah.
It's when that guy was plotting where the water sources came
Yes.
from for a disease. I can't remember which
Exactly. It was John Snow who was trying to map the extent of cholera in London. So what he did is every single one of these dots represents someone that died of cholera, and these crosses, which are a lot bit harder to see, represent a water pump. And he realised that all of the dots are congregated around this one cross in Broad Street. So he marched down there and he took the pump handle off from the pump, and everyone stopped dying of cholera. And they still have a lecture every year where they ceremonially go back to this pump and they take the handle off and they march off and give the lecture and so on. But it shows how we can, just by putting something on a graph, it can reveal stuff that we might not otherwise notice. So at the start of this talk I said it's not multidimensional data, but what is multidimensional data? So it's anything with more than one variable. So a list of people named Matthew is just one-dimensional, right? It's not providing us very much information. But a bar chart of people called Matthew and their heights is 2-dimensional, right? We've got a name and we've got a height. And if we plot the height of the Matthews against the net worth on a logarithmic scale, well, this is 3-dimensional data because we have these labels as well. Obviously, it's kind of warped by the difference in financial resources there. So before we go on, I'm going to talk a bit about what makes a good graph. Has anyone heard of this book before? Yeah, a couple of people. It's a very famous book, it's very good, but it's good that you guys haven't heard it because you're going to think this is all very original now. It's by a guy called Edward R. Tufte, who is a statistician and political economist. And it's all about different ways of representing data, what's good, what's bad, what's interesting, and so on. So he also has a nice section in it on history of graphs. So this here apparently is the earliest ever line chart. Can anyone guess what this represents just by looking at it? It's quite small and it's obviously not very clear. Have you got any thoughts on what this might be trying to show us?
Some horizon set.
Almost, yeah. So
Position of the stars?
yeah, it's trying to show the position of the stars throughout the year. So you have Venus, Mercury, I guess that's Saturn and so on, and they're kind of crudely plotted on this. And this was in a book by a guy called Macrobius Boetius, which is a great name, in the 11th century at some point. And then there's like a whole lot of nothing for about 600 years, right? And then you get 2 guys coming along who are called, the first one's called William Playfair, right? Who's described in one biography as an engineer, political economist, and a scoundrel, which is a really fun description. He was originally the assistant to James Watt, who invented the steam engine, and then he went to France to storm the Bastille in the Revolution, and then he came home and just made a lot of graphs trying to argue about deficits and so on. And he kind of pioneered ways of presenting economic data largely. So this is one of his kind of most famous graphs where he's plotting relative imports and exports of between, I think it's from the UK to Denmark and Norway, and saying how there used to be a kind of trade deficit and now there's a trade surplus and so on. But he invented a lot of the charts that we all kind of know and love today. Like he invented the line chart, arguably, the bar chart, the pie chart as well. So back when he was doing this, it was a much more laborious process, right? It had to be engraved on a slab and printed and so on. But yeah, he really laid the seeds for a lot of what we see today. He also had J.H. Lambert at a similar kind of time, He was a mathematician and a scientist, and he was, whereas William Playfair is using charts to kind of represent his opinions almost, what Lambert was trying to do was use these kind of graphs to figure things out. Can anyone guess, you haven't really got much information, but can anyone guess roughly what this might show? The only information you've really got here that's useful is what's on our x-axis, these individual letters that are cycling through. It might be too far away for most of you to read them. Any guesses what those letters might represent?
Months of the year.
Months of the year, yeah. So he's plotting here the temperature of the soil over the months of the year. And by plotting these individual points, then you can start looking at kind of fitting and all that kind of stuff. So now we're going to rattle through some of the examples in Tufts' book, and we're going to decide if they're good or bad charts, right? Obviously, this is kind of up to your opinions, but we're interested to see. Okay, this chart. First off, again, can anyone figure out what this represents? It's a very, on the back?
It's a French train timetable.
Exactly. It's French train timetable. So on every one of these lines, you have a city, right? And then each one of the vertical lines even represents the time that the train will be leaving a city and traveling through it. So if you're trying to figure out when to get the train from Paris to Dijon, then you realize that you're going to get on the train at however much past 6, and you can follow this line all the way down, looking at how it stops at every station, right, and figure out you're going to be in Dijon at half past, just after 3 o'clock. What do you think? Good chart? Bad chart?
I like it.
Like it? Yeah. I think it's good. It shows a lot of information in an easy to understand way, right? And I feel like if that's up on the wall of the train station, you'd be able to figure it out, right? Even if you can't read, which some of the people back then wouldn't necessarily be. I suppose you need to be able to read the names of the places, so maybe that's not a fair point. Okay, what about this chart? Good chart? Bad chart? So yeah, this chart is about how much it costs to look after the mentally unwell in America. What do we think? Is this good or bad as a way of representing information?
Yeah,
It's all right.
It's
okay.
okay. So it might seem like it's okay, and then you look at the numbers, right?
Yeah.
And you look at how this one here is $213. Is that per? I guess it's $230 per year. Whereas this one is $214. It's only $1 more. But if you look at the relative sizes of that, right? So one of the things that Tuft, one of the metrics he came up with was the kind of lie factor. Like if you look at the proportional sizes of these things, how big a lie is being told. Because if you were just to be given these sizes, you would probably say, okay, well, this one here looks like it's less than half the size of the one at the end, when it's not that level of kind of difference. So this is what he would call a kind of bad chart. What about this one? Again, we've got to look quite carefully for the kind of trick here of what's being done to lie with this chart. I guess that's kind of the hint it's a bad chart, but what can we notice? Well, first of all, if you try to think about what this chart's trying to say, what do you think the chart is trying to communicate with these lines?
The United States doing well in Nobel Prizes.
Yeah. But what's it trying to kind of represent about the kind of recent developments in that? If you look at the kind of trajectory of the chart graph, right, you can see that it looks like, okay, well, what's happening? No one's getting any Nobel Prizes anymore, right? It's gone from up here at kind of 25, and now it's all the way down at kind of 12, right? Which obviously, oh no, very terrible with what's happening. But then you look at the kind of the labels here, and each of these labels represents a decade, right? Going on here. And then this last one is between 1971 and 1974, right? So that represents 3 years, right? Which means that if you were to correct this for the whole decade, it's probably about the same, right? It's got 40 Nobel Prizes in 3 years compared to 25 in 10, right? So this is a bad chart, right? Okay, this one is very famous. Has anyone seen this before? Cool. So I'm gonna describe this because the text is very small. But this shows the invasion of Russia by Napoleon in 1812, 1813, when he entered Russia with over 400,000 men, and it shows how, as he travels along, his men kind of disappeared, like desert, die, and so on. And then it shows his journey back from Moscow, going all the way along here until he crosses the river that he had left with 10,000 men, and it initially invaded with over 400,000. And it shows their position in kind of 2D space, but it also shows the relative size of the army, the direction they're traveling, and the temperature across all of these. events. And you can kind of see what's happening here. People are dying because they're cold, right? Which is the whole story of that kind of invasion. What do we think? Good chart? Bad chart?
Pretty good.
Pretty good. According to Tuff, this is the greatest chart ever made, right? Obviously, this is a highly kind of, it's a highly subjective thing. How about this one? So this one here, if you can't see it, it says age structure of college enrollment at the top. Then you have these two sections, 25 and over and under 25. And it's plotting the relative percentage of total enrollment in American colleges. What do you think? Bad? Well, why is that? What do you think
I
is
don't know
that?
what it's telling me.
Yeah? Okay. Anyone else? Any thoughts on it?
Of that break line,
Yeah, it's got a break.
34 to 66, it's
Yeah.
a massive gap. So if you did it to scale, it would be quite different.
Well, according to Todd, this is the worst chart ever made, right? Because what this is showing, it's got this kind of 3D effect on it, right? But really it's just showing 5 pieces of information, right? Because you have 5 points on each of these lines, but this is 25 and over, and this is under 25, right? So all of these percentages sum up to 100, right? So it's taken 5 pieces of information and made it into this kind of thing that looks nice, but yeah, according to Tufts, worst chart ever, right? And finally, this is another one. What do you think about this one? This is trying to show the relative purchasing power of the US dollar across different presidents. So we start with Eisenhower, where it's worth $1, and then we look at Carter, and it's worth 44 cents. What do we think? Good chart, bad chart?
Is the problem going to be the area versus the length?
Exactly, yeah. So what this is doing is it's representing the relative purchasing power of a dollar through length, right? But even though this one is 44% of the length, the area is going to be substantially less. And when we're looking at things, we're interpreting the area, right? So comparing the size of this to that, it looks like this dollar is worth 25% of what that one is, when really it's only worth 44%. And cool. So Todd came up with kind of 5 principles, right, for kind of graphs, which was, above all else, show the data, maximize the data ink ratio, erase non-data ink, erase redundant data ink, and then revise and edit. Data ink, by that Tough means anything on the graph that's not showing the data. So ignoring these principles, we're going to rattle through a few of his kind of graphs, and you're going to tell me which one you think is better. Do we prefer the left one or the right one? These show the same data. So hands up if you prefer the left chart, and hands up if you prefer the right chart. Okay, that's overwhelming. Okay, how about this one here? Hands up if you prefer the left one, hands up if you prefer the right. Well, sorry, just hands up if you prefer the left. Do more. Cool. Okay, who prefers the right? One person, yeah. Cool. Finally, he prefers the left. And who prefers the right? Cool. So all of the ones that you guys didn't like were the ones that Tuff drew in his attempt to kind of improve charts, right? But if we go back to his principles, I think it seems like you can kind of see why. In that, one of the reasons that he gave that people might not like his charts is because they're unfamiliar, right? Everyone's seen a bar chart, but they haven't seen his image. But I don't really like that explanation. I do think that it's perfectly reasonable to prefer the ones before he's improved them. But if you look at his kind of his principles here, 3 out of his 5 principles are about minimizing the amount of ink that you end up using, right? This guy's making graphs back in the 1980s, right? When he has to draw every line on the thing manually, right? So it feels to me like you can't separate his thoughts on things from the process by which he made it. It's very laborious for him to draw every line and color everything and all that kind of stuff. I think the point I'm trying to make here is that it's much easier to identify a bad graph than it is to identify a good graph, or to decide what a good graph is. It's obviously very subjective. But we don't have to draw our graphs, right? We can use all sorts of technology now, right, which makes our lives a lot easier. You can use Origin, you can use Excel, or if you're using Python, you can use graphic packages like Matplotlib and Seaborn. Does anyone use anything else for making graphs? Yeah?
ggplot.
ggplot, yeah, cool. So yeah, but there's all sorts of options now that don't involve getting out the graph paper, which is good for us, right? So now we're going to run through the kind of different dimensions that we can include on a graph. So if you've seen this talk before, don't jump out. This is a famous data set. I want people to try and guess what the data set is as we add more and more dimensions to this graph, right? So on our y-axis we have the common depth in millimeters, and on the x-axis we have the common length, right, for all of these samples. To add a third dimension, we can plot the body mass of each of these measurements, which is between 3,000 and 6,000 grams, which is represented by the size of the circle. Feel free to shout out if you figure out what this represents. And we can also plot the species of our measurement here. We've got Gentoo, Daly, and Chinstrap, which is represented by the colour of the points. Has anyone got it?
Penguins.
Penguins,
Oh.
yes, this is different penguins. We can increase the dimensions to 5 by adding different markers to kind of the different islands these measurements were taken on, Biscoe, Torrington, or Dream. We can add a 6th dimension by keeping the rest of the stuff the same, but making it have a black outline if it's a male, or if it's a male, and a non-black outline if it's a female. And we can add a 7th dimension by adding a kind of flip our length, a 3D plot. But this is too many dimensions, right? At some point along the way, we've lost sight of what we're trying to represent, and we're just putting stuff on a graph, right? It's us trying to show what you can do with a computer, rather than trying to show a piece of data, right? So for those that don't know what a culmen is, it's the part of a penguin's beak, right? And it's different in different species. So 7 dimensions is too many dimensions, right? When we're putting stuff on a graph, it should be immediately obvious what people are looking at. Potentially we can split stuff up into individual graphs, and that's easier for you to interpret. We've still got lots of information here, but just by separating it out by species, and then having individual plots with the different islands on, it's a bit easier for someone to look at it and immediately understand. We can also use redundant dimensions here, where here both the colour and the marker are representing the same thing. So a blue circle is something from Biscoe, and an orange cross is from Dream. But by having that differentiation, it's easier just to look at the graph and figure out what's going on, instead of giving someone homework to do just to understand how you've represented the data. There's also redundant dimensions here, where we have distance in x and y, and we have counts per second for the radiation detector, and colour representing the same thing. But it allows us to kind of understand what we're looking at a bit more clearly. So the other, the colour here is hard to discern. But 3D plots in general are not always the nicest of ideas because of how they warp kind of perspective, right? It's hard to distinguish between these two colours, but these two segments of the pie chart should be identically sized, right? And on the 2D representation, it's easy to see they are the same size. When you look at it in a 3D thing, the perspective is warping the relative size of our chart. So in general, 3D charts are not the way to go. The one exception to that is maybe if you want to interact with it yourself, because then you can explore the data, and just adding that movement to it can make it easier to see what's going on. But there's always obviously a distinction between representing information on a screen and representing it in a paper or something like that. If you can actually interact with the data, it's easy to understand. So obviously, 2 parts of any academic thing is kind of going to conferences and writing papers and so on. And I don't know if you guys have been to many conferences, but sometimes they can be like really quite dull, right? And it's a big kind of topic of conversation that conferences can be like really, really boring, right? And maybe we should like try and do stuff that's a lot bit more interesting, right? So what I'm going to show you now, I'm not going to claim this is actually the best way to represent this data, but it is at least more entertaining, right? So we're going to talk a bit more about using different sensors to kind of present data. So the first thing that we're going to have a look at is how we perceive texture, right? If you've looked at a board, and we've had our fun there, but at the end of every table you should see one of these little pieces of plastic. Unfortunately, there are issues with printing the kind of housing, so you're going to have to play along here, right? On the back you should see letters A, B, C, and D. So I want you to kind of pass these along and then feel under each of these letters, right? And in a second, I'm going to show you a graph, and you're going to try and tell me which one of these graphs you think this represents, right? So just keep an eye on the letters here. Let me move over to the graph so you can have a think about it. So yeah, we've got 4 different options. I want you to just have a feel of your bit of plastic. There should be one on each row, and then you can have a think about which might represent which graph, and then you can make some guesses. Bear in mind there's units on these graphs, so you want to keep an eye on the units as well. Not units, there's numbers, there's not units. you guys got thoughts? You can wait for other ones. Or is it impossible to tell?
I've narrowed it down by half.
Is that right? How do you get it? Up to that stick. Yeah, I'm just waiting for that one to finish.
So is the task which one of these?
Which one of these graphs represents what you've just felt? Have you got any guesses? Two? Have you got a reason for thinking it's two, or?
How dotty they were?
Yeah, potentially. Unfortunately, that's not the right answer.
So two.
I say four. What do you say? It's four.
Seems to be more in A, and it isn't two.
What is that?
There seems to be more in A.
Okay. Yeah.
Yeah, that's what I was.
Yeah. Okay. So there's technically two correct answers here, right? It can either be one or it can be four, right? So if I show you what this looks like, you can actually look at the other sides now. We have a bunch of squares here, right, that you're feeling. So it depends on how we're interpreting this texture, right? If we're counting the number of squares in here, then we're definitely looking at number 4, right? Because we have 298 odd squares there, and then less in here, and so on. But if instead we're representing the size of each square, then it can equally validly be number 1. But yeah, I think we can kind of conclude this is not actually a very useful way to represent information, but it is fun. So now I'm going to talk a lot about some of the data that I kind of gathered in my PhD. So this is a sensor unit that I kind of worked with and developed kind of software for and so on, which was a laser scanner unit that you'd carry around the place with several radiation detectors, and it would pick up the physical contours of the environment and also the radiation as you walked around. So this is some data that I collected in Chernobyl. This is the unit 3, so it's right next to the one that exploded. So you can see here the kind of point clouds, and you see the detail that we get, kind of banisters, and then these individual radiation measurements that are kind of scattered around the room. So in this case, we're going from a kind of blue to a red is the level of radiation measurement. So this corner of the room is, or this end of the room is very bad. It also, on these representations, if it's got a white square around it, it means the radiation is so intense that we can't actually record it on the detector we used. But yeah, this is all well and good, just looking at it. But like again, maybe we can go further. So the first thing I did is we take a bunch of these radiation measurements, right, which are counts per second at any one particular position, and I tried to convert them to sound, right. So our radiation measurements go from 700 counts per second to 5,000 counts per second. So if we map each of those measurements onto a frequency, right, it will range between 200 Hz and 2000 Hz. We generate a bunch of sine waves and we smash them all together. Then we get this. So you see that we have the kind of counts per second on the y-axis and then our time on the x-axis. And a lot of red dots representing which measurement we're listening to. But this isn't particularly pleasant, right? This is just a bunch of random frequencies that we're all kind of jammed together. So this is all being done by a computer, right? So instead of using just frequencies, we can use MIDI, right? Has anyone ever had like a keyboard, right? You can translate each one of these measurements to a piano note. So on the MIDI system, it goes between, I think the highest note is like 86 or something. Each note is represented by a number. So we can easily map from counts per second to a MIDI note in a kind of common Python package. And then we can play our MIDI file using something like Audacity. You get the same information but in a slightly more musical kind of sense, right? I'm not going to make listen to the rest of that. But finally, right, to make it even more musical, does anyone play a musical instrument? Has anyone heard of like the pentatonic scale, right? The pentatonic scale is very easy, right? It's 5 notes. And everything sounds kind of nice in the pentatonic scale, right? You can just go up and down, it sounds like you know what you're doing, right? So if instead of just mapping, if we take all of our MIDI notes and we map them onto the pentatonic scale, then we can make something that's more musical and more pleasant to listen to. And here you can see the actual measurements. Cool. So the final thing that I wanted to do, right, is that this sound is one of the most efficient ways of transporting information, right, in terms of the energy that we put in compared to how far you can transmit information. But we transmit information in a lot of ways in sound. There's obviously pitch, which you just explored. There's also kind of timbre and tempo, whatever. So the final thing I wanted to play with is, and instead of mapping our counts per second to a pitch, we can map it to a tempo, right? We can go between 75 beats per minute and 180 beats per minute. If we did that with every single measurement, it would be kind of a mess. So instead we can chop up our measurements, we can average them, and then we can take an audio file, we can slice it up into little sections, stretch them or compress them to suit the tempo we want, and then recombine them all together. That's when we get something like this. Cool. And with that, have we got any questions, comments, views, or thoughts? Yeah.
I think first we should give a round of applause.
I'm assuming that was a robot that went in to Chernobyl and you were outside.
No,
somewhere?
that was actually me. Yeah, the robot that we tried to bring had some technical issues, so they thought, let's just make a PhD student do it. But in terms of the parts of Chernobyl, that one is, you obviously wouldn't want to live there, but if you're just going in for like a few minutes, so that bit isn't particularly.
You had lots of
particularly
lead aprons and
No,
stuff.
no, that's, PhD students are cheap, right?
On those last couple musical ones, I didn't quite follow the spatial pattern. That was
Oh,
being
sorry,
shown.
I should explain that in more detail.
It seemed to be just following around in
Yes,
order, right?
that was.
But I guess
well,
it isn't.
Yeah, it was. So it is. So what we're showing here is these measurements are already on the. That's all the measurements that are taken, right? And then the circle is visiting each of them. But really, this is the path that I was like walking out, right?
Okay.
I was walking out as I kind of covered the space, so potentially it would have been clearer if they're being deposited by going around. But in terms of our black points are kind of two-dimensional space, the projection of the room, and then each of these colour points is an individual point of measurement. But yeah, it may have been clearer if they were deposited as kind of walk around the space.
Were you aware of those readings as you were going around?
Yes, kind of. There was someone shouting at me in the corner from a laptop.
You say run away. Is that when you?
Well, there wasn't really any choice of running away, really, unfortunately. I think if we pull back through, you can probably see at one point, you will see the kind of ghost of the laptop man standing in the corner. You can't really see him, but that blob there is one of the other PhD students. Yeah.
It's good they put them somewhere that wasn't a red zone.
Yeah. When we didn't really know where the red zones were when we met in the room. That was part of why we were there, right?
Feel brave.
No.
Have you thought about like patenting pentatonic Geiger counters or something?
Yeah.
The thing is, it's one of those things. I don't know if it's actually a very useful way of because it's kind of it's what Geiger counters already do, right? In a way.
Yeah.
Like,
Yeah,
the
this is
cheapest
what I was
ones are
thinking.
just a series
Yeah.
of clicks, right?
Yeah.
But then you have to find a bunch of workers with perfect pitch, right?
Yeah.
And say, oh no, that's a.
Apparently, if you've got perfect pitch, you can't tell the difference between octaves. Some people,
Really?
Oh, okay.
supposedly. Yeah.
Fair enough.
So more generally, if someone's got some data and they want to plot a graph to show something, what would be your advice to them for starting to write any code like those? You show packages that we all write, we all generate graphs in that. Have you got any sort of words of wisdom that you've picked out from?
Yeah, it's a good question. I think the real thing is if you're using one of these plotting libraries, particularly something like Seaborn, get up to the list of different things. These plotting libraries, and the same thing with most libraries that you'll use, are generally made by people far cleverer than really any of us, right? Who have spent a lot of time figuring out the kind of best ways of doing stuff, particularly stuff with Seaborn, but Seaborn itself is just a kind of something that goes on top of Matplotlib, right? which is built with a particular style in mind and themes and so on and stuff like that. So by using these libraries that already exist, we can kind of take advantage of a lot of the kind of thoughts that people already put in to the best ways of representing data. And the nice thing about doing stuff in one of these more common languages like Python is there's so much information online about the best ways to kind of do things and advice and stuff like that, where there might not be for stuff that's a bit more obscure. But yeah, even stuff like Excel can definitely make graphs easily, but then the question also becomes with some graphs, it's one thing to make a graph, it's another thing to be a graph that's kind of worth making. So if you can look at a graph and you can figure out what story it's trying to tell instantly, then that kind of shows that it's probably a good graph, as long as it's not lying to you. But I guess the other issue is you might become blind to that. If you already know what's plotted on a graph, like if I go to one of these ridiculous kind of convoluted ones, I can understand this instantly because I've made it and I've looked at it like a reasonable amount. So potentially it's worth showing these things to someone else who isn't necessarily as bought into what you're doing as you are already, so then they can say, okay, well that makes sense to me, or well that doesn't.
Maybe it's sort of specific to the audience.
Yeah.
I guess who's going to be looking at them, whether it's
Yeah.
what you should do. Yeah.
I was going to ask, just to sort of follow up on that, but so some of the graph sort of examples you showed us were very kind of, I was just thinking like the size of the dollar bill kind of.
Oh yeah.
Whether or not they were good or bad ones, they're very kind of customizable. And my like knee-jerk reaction looking at them was like, I'd almost argue like whether I was thinking like, does it even count as like a chart? I guess it is data visualization.
Yeah.
But like, do you think this is something that can be done well, or do you think this is kind of a waste of energy to visualize something like this, or the other one, the funding for it?
Well, it's one of the things that Tuff kind of pushes back on what in his book is that he thinks that the reason that everyone makes these graphs is because there's a perception that like statistics and data are boring, right? And that if you just make something that looks nice, then people will be interested in it. But even though I don't necessarily agree with some of his like static ideas of a good graph, he definitely does make the point that if you're showing something interesting in a fairly simple way, then even people who aren't necessarily that adept at kind of maths or statistics or whatever can be interested in it as well. But the issue is that the people making all these graphs are probably fairly good at statistics, and they're just choosing to make a choice, which is to lie.
yeah, for sure. Okay.
At the beginning, you showed Tuff's rules about those 5 points. One of them was sort of like remove non-data ink. Erase non-data ink. And you said, maybe in his time when you were drawing things by hand. Can you kind of suggest any more modern revisions of those, maybe something to do with information density or what you're showing?
Yeah,
like
I don't know. It's I haven't thought about kind of compacting it into kind of rules, so to speak. But one of the things that Tuff kind of is really clear on in his book is that even though he lays out these kind of rules and stuff, he says it's always permissible to break these rules if you think the graph is interesting, right? And he's like not dogmatic in that way. But I think even though I think everyone's perception of what is a good graph is going to vary, I think by reading a lot of different people's ideas about what's a good graph, you can have that at the back of your mind. So even though I don't agree with all of his thoughts, I don't agree with a lot of other people's thoughts on it, just if you're bearing something in mind when you're making a graph and you're saying, is everything on this graph actually showing information? I think that's definitely a kind of useful way to look at it. Even if you're deliberately breaking these rules, at least thinking about them when you're doing something means you're putting in more thought than some people.
Thank you.
Any other questions?
Yeah, have you shown those sort of audio clips or anything to anyone at conferences or like non-experts?
Yes, yeah. I made a not these specific ones, but I made a kind of slightly unnerving kind of spacey kind of sounds for some mapping we did in a cave in Arizona. So as you travelled through the cave, you'd hear like kind of I think it was like a synthetic organ that was like a tone of thing. And again, it's the thing where you'll have that in your presentation, and then people will come up to you a few days later and say, "Oh, you're the guy with stupid videos," or
Have you shown it to sort of experts and non-experts? And do people take it differently? So do experts see it as like a quirk maybe, or do
I don't
they get
know.
people interested who otherwise might not be?
Yeah, I guess it's kind of like a sampling bias in a way where it's like, I don't know if people that saw the presentation went home and said to their wives, "Oh, some guy had the stupidest talk ever at the conference," or whatever. But people have always been very nice to me about them. But yeah, no, it's mostly been in kind of conferences and stuff, so it hasn't been to like hasn't been to complete neophytes at any point.
I was just going to ask, other scientific posters, what do you have any top tips for making a poster really good?
Yeah, well, I think sometimes people just bring props along, right? Which is always fun. Like the good thing about my kind of work is at most times I had to do a poster, I would just bring along my scanning equipment, and then be like, "Oh, do you want to just play with it?" And then they'd make a little map of the cropping space. Like, "Oh, that's really interesting." And even things like these, like bits of kind of plastic tap, like again, they're not necessarily a useful way of representing data, but they are an interesting one. So just kind of thinking about that aspect of it instead of just filling your kind of poster with. It's obviously good for your poster information, but it's also good to have some kind of peanuts to lure people in with, right?
I'm not an expert, I'm actually from research development, so
Yeah.
but I just had an observation. The thing with the sound of it was interesting is that it kind of, you dictate the journey of the viewer or listener,
Yeah.
whereas visual, you're freer to.
Yeah, it's
jump
true
around.
actually. Yeah. I guess that's a good and a bad thing in some ways, and it's almost nice to have everyone be looking at the thing you want them to be looking at. It's like a director having one thing in focus on the screen.
Yeah.
Yeah.
I guess if it, as you talked about the 3D graphs that you can rotate if you're at a computer and you can control it, I guess you could do something where you could move that point, right?
Yeah,
So
definitely.
you can kind of explore it yourself.
Yeah. It's one of the things that I always wanted to do is kind of put some of these things in kind of virtual reality, and then like people could move around the space and listen to this music that is functionally pointless, right? It's not going to kind of, it's not going to get any PhD really. Any other questions?
Yeah, I think we should thank Matt.
Thank you very much.